Good morning students. Once again in the class of Physics 11th standard of kinetic theory, we will discuss about the law of equipartition of energy. In this, the kinetic energy of a single molecule is given by Et is equals to 1 by 2 mv x square plus 1 by 2 my square plus 1 by 2 mz v square vz square equals to 1. For the gas and thermal equilibrium at temperature T and the average value of energy denoted by Et is given by 1 by 2 mv square plus 1 by 2 my square mvy square plus 1 by 2 mvz square is equal to 3 by 2 kb. Equation number 2 we have taken since there is no preferred direction. Equation 2 implies that 1 by 2 mv x square plus 1 by m is equal to 1 by 2 kbt. Y will be 1 by 2 kbt and z will be also equal to 1 by 2 kbt. So we will have this equation given by this equation, and the molecules free to move in a space needs their coordination to specify its location. So if the constants is moving in a plane, it needs two, or if the constant is moving along a line, it needs just one coordinate to locate it. This is also called expressions expressed in another way. We say that it has 1 degree of freedom for motion in a line, and 2 for motion in a plane, and 3 for the motion in the space itself. Motion of a body on a whole as one point to another is what we call translation, and the molecule move from free to move in a space that has 3 translational degree of freedom. Each translational degree of freedom contributes a term that contains the square of some variable of a motion is 1 by 2 mv x square, and similar terms is vz and vy, and we have thus the thermal equilibrium, that is average of each such term is equal to 1 by 2 kbt. Molecule of a monoatomic gas like argon have only translational degree of freedom, and thus by what a diatomic gas will have O2 and N2. A molecule of O2 has the 3 translational degree of freedom, but in addition it rotates about its center of mass and shows the 2 independent axes of rotation 1 and 2 normal to the axis joining the 2 oxygen atom about the molecules can rotate. The molecule has a 2 rotational degree of freedom, and each of this contributes a term of the total energy constitute of translational energy, that is Et and rotational value. If they have 2 degree of freedom, they will have this particular value, that is Et plus Er is equals to 1 by 2 mv x square plus 1 by mv x vy square and 1 by 2 mvz square is equals to 1 by 2 I1, and omega 1 is equal to the power 2 plus 1 by 2 I square omega 2 square is equal to the first equation. They have just like this, they have the 2 degree of freedom here. Now omega 1 and omega 2 are the angular speeds along the axis A1 and 2, and I1 and I2 are corresponding moments of inertia. Note that each rotational degree of freedom contributes a term of energy that contains the square of a rotational value of motion. We assume that O2 molecule is a rigid rotator and the molecule does not vibrate. This assumption, though found to be true at moderate temperature of O2, and is not always valid. Molecules like CO, even with a moderate temperature, has a moderate mode of vibration. It oscillates along the intermolecular axis and with one-dimensional oscillation, and contributes a vibrational energy of EV to the total energy, which is also given by EV equal to 1 by 2 mv vy square plus upon dt square plus 1 by 2 1 ky square, which is given by this particular equation. Now we will have already told you about this O2 molecule, CO molecule, or the atoms rotate in the one-dimensional oscillator, and thus it is given by this particular value E equal to Et plus EV, Er plus EV equal to this equation, this particular equation. Now this is equation number 5, okay, and thus this K is the force constant of the oscillator and Y is the vibrational coordinate. Once again the vibrational energy terms the equation that is the previous equation, that is equation number 5 itself only. This particular equation terms square terms of vibrational variations of motion y and dy by dt. At this point, notice one important feature in 13 point in fifth equation. Rotational degree of freedom has contributed only one square term and one vibrational mode for two square term, kinetic and potential energy. Each quadratic term occurring in this expression for energy in the mode of absorption of energy by the molecule. We have seen that in the thermal equilibrium at absolute temperature T, for each translational mode of a motion, the average kinetic energy is equals to 1 by 2 kB2. As I told you, that is it is from the law of equipartition of energy, so it will have the same value for x, y and z value. And thus the most elegant principle of classical statistics mechanics, first proved by Maxwell, states that this is for each mode of vibrational, translational, rotational and vibrational, that is equilibrium, that is total energy is equally distributed in all possible energy modes, which each mode having an average energy equal to 1 by 2 kB2, which is known as the law of equipartition of energy. According to each translational rotational degree of freedom of a molecule contributes 1 by 2 kBt to the energy, while each vibrational molecule contributes 2 into 1 by 2 kBt is equal to kBt itself. And since the vibrational mode has both kinetic and potential energy nodes, the proof of the law of equipartition of energy is beyond the scope of this. Here we shall apply the law of predict and specify heat of gases theoretically. Later we shall discuss briefly the application of specific heat of solids. So this is not possible to have this particular thing. The two independent axes of the rotation of a diametric molecule is being given in your book itself. Go through that. If they have the three axes, they will have the three motions, they will have the three directions, but here the direction is not being given. No preferred direction has been given to you here. So this is the reason why it is law of equipartition of energy cannot be proved here by this particular book itself, and thus it has been given by some major idea about this law of equipartition of energy is being given here, so that you will be able to understand what is the law of equipartition of energy. Now, specific heat capacity of a monoatomic gas, we will discuss about diatomic gas mean free path, and thus this chapter will be finished, and we will be discussing the oscillations chapter after completion of this particular chapter, and we have only 2 chapters left. Oscillation, after the oscillation we will have the wave chapter, and your portion will be finished of this particular session of 11th standard. So these two are very important chapters, as is oscillation and wave. So looking forward, in the next video we will discuss about diatomic molecules and monoatomic and molecules itself, in which I will tell you about the variations, how they have the direction or not, they will have the direction or not, how they are interpreted, and many more things related to this topic. Thank you, students.